In this short video, I'm going to show you how to create several types of RNA-seq pipelines and how to use the different options in these different sections that you see on the screen after I have already uploaded the raw FASTQ files either directly to the platform or using a reference SVL file. Now what we're going to look at is what is the logic behind different combinations and how do I achieve specific targets with these pipelines. So my first button is always going to be start, and then I'm going to do the simplest thing. So the simplest thing is to take my raw reads in raw FASTQ files and use bowtie to T mapping on transcripts, and then transforming the mapping into a gene expression table. Now this table is going to have gene IDs and isoform IDs from the known GTF file. So whoever did the assembly put together a file that lists the beginning and the end and the different variations and names of all the possible genes and isoforms on that genome. So if I click end, I am going to have this pipeline. So I'll do cancel, and now you can see the pipeline. Now I can also right click on each step, and then I will go back to the start. And now let's look at the same pipeline but with some pre-processing options. So again, I can go to Trim-O-Matic, which will reduce the adapters, PCR clean, removing the duplicates from PCR amplification, go back to bowtie to T, and then RSM expression table, and then I will do end. So this is another simple version, the same pipeline, but with some pre-processing steps. Now you can see that after this step, after I have the RSM expression table, I can also create a separate exon table. And now I will have two output files. Let's do that again and just read the description. You have exon expression, another file, in addition to your expression of genes and expression of isoforms. Okay? Now, also, I have an option to do differential gene expression. So once I have the table of expression, I can do other downstream analysis with the table. And so here I can use something like DSEC2 or EdgeR. Okay, and then I will click on end. Now what if I go back all the way here? Let's remove all of this. And let's do a more detailed analysis of the elements that we have without relying on the GTF file provided to us by the people that assembled and annotated the genome. So what would I do? I would start again here, and then I can go to bowtie 2G, and then BS exon, which will map the exons, and then I go to GTF adjust, create an adjusted GTF file. Then I can use bowtie to I. Bowtie to I will map on junctions. Then I would use isolasso, which will create the isoform. So now I have isoforms. And then I will merge these new isoforms into the old GTF file. And then I can do bowtie to T, mapping on this new GTF. And finally, RSM expression table, and this is a more complex, expanded pipeline that uses my custom configuration to get a more detailed view at various elements, also those that are not known, and some are them putative genes that could be expressed. And again, I have the option to separately look at exons and separately do differential gene expression. Now let's go back. In fact, we will go all the way back to here. Okay, and now let's start. What does Tophat 2 do? So Tophat or Tophat 2 is the same thing. Essentially, it does these three steps in its own way. And it's considered to be somewhat of a gold standard. So what I can do is I can go ahead and click on Tophat 2, which it doesn't have a description, you notice, but that's just because it's exactly the same as Tophat. So I can do either one of those. Tophat is just a newer version of Tophat. And then I can go cuff links, cuff merge, bowtie 2T, and now I can go to RSM expression table. That is if I want to have an expression table. Now what if I don't want an expression table? Then I can go from cuff merge and go directly to cuff diff, and then I will just get a differential gene expression. And as you saw, let me show that again, we already have the false discovery rate threshold. Now if you go to Transcriptomics 2, you will see there a whole description of what false discovery rate is, and this is going to be important for your cutoff for the differentially expressed genes. Okay, so all the same things, of course, could be done after Tophat 2. You can go back. In fact, let's go back all the way over here. And now you understand the logic. You have the step of mapping on genome, the step of identifying exons, and then mapping on junctions, creating isoforms, processing that back into the GTF file, mapping on transcripts, and creating an expression table. Now sometimes there is a completely different problem at hand, and we have a non-annotated genome, or the genome is not very well annotated. Maybe the assembly wasn't done very well, and we're interested in using that genome and just identifying which areas are highly expressed so that we can try and annotate those. So what would we do? We would again start over here, and then we would go to bowtie 2G. Okay, and now you can see that we have an option to do segmentation. And in segmentation, we're not going to go too much into this pipeline because it's used for very specific cases, but you can actually select very specific areas that have a high expression level . You will update again the GTF. You will create an expression table. You will do the segmentation on that table, and then you can use those reads and do blast X. So blast those sequences and try to annotate. Now this is a very complicated process. It will require a very specific situation, so that's why we're not really going into detail about the segmentation and annotation parts. Now another thing that you will notice here is that all of these files, the pre-processing files, are essentially going to work with a lot of your options right here. And that's very important so that you know that for every type of pipeline that you do, you can add some of these. Now, what is this error correction section? The error correction section is actually useful for poorly sequenced files and for microarray files, and that's why it was added here. Now, in most cases, you're not going to be using this. This is a very computationally expensive pipeline to run, and so only use it when you know how you will analyze and evaluate your results. Another section that we didn't cover here is the data simulation. The data simulation allows you to generate reads and test different options, different pipelines, using mapping the raw curve for different steps of the way to generate those curves, compare different methods. Now we're also not going to go into how to create a pipeline like that because our focus was how to generate a number of simple RNA-seq pipelines that you could use to analyze your data. Now in the next section, we will try to cover a little bit more about the different options for differential expression and how to analyze the table that you get as a result of these pipelines.